In this video, we're going to talk about vector spaces. Vector space is a concept that is inherently extremely important in mathematics, and the first time most people encounter it is in a first semester linear algebra course. So it's not the most exciting topic in the world, but it is extremely important and valuable for a set to be defined as a vector space. So what is a vector space? Well, it's actually pretty simple, and we won't give this a whole ton of treatment, just at a really basic level, but a vector space is a set. And we'll just call that set V. Now, we'll talk about sets in just a moment, but it's a set V on which scalar multiplication and addition of its elements is defined. Then the result of such operations should produce an element that is still in V. Okay, so let's actually describe what we're talking about here more specifically. So a set is any collection of elements. So a set is simply a collection of similar elements. Okay, now similar is a very abstract word because similar could mean different things in different cases. They're similar in that all of these elements are collected together. Now, common sets that we've probably encountered before are, for example, the set of all real numbers. The set of all real numbers. Okay, so fractions, decimals, zero, negative numbers, just integers in general. We also have other sets that are specific subsets of the real number set. For example, n is used to describe the natural numbers. And the reason we call them the natural numbers is because they are typically the numbers that we count with. So depending on who you ask exactly, these typically start either at 0 or 1. Here we'll just go ahead and define them as the counting numbers 1, 2, 3, 4, etc. So no negative numbers, and we won't include 0 in this set. Z, or script Z, now notice that we're using what we call a script R or a script N, and they kind of have this double line somewhere. This is the set of all integers. The set of all integers. Okay, we can also have other specific types of sets. Now the way we define them is using what's called set builder notation. Set builder notation. And it's just a notation to really compactly express what we're talking about. So for example, we have a set builder notation, then we have just kind of what we call the set element notation. Okay, so they're very similar. The set builder notation is much more powerful in general, but let's say I define a set, and I'm just going to call this set capital X, and the elements that I'm going to put in there are the names Bob, Sally, and Jane. Okay, so that's a set of 3 names. And set builder notation, so this actually lays out all the elements. We could also describe the natural numbers this way. We could say that the natural numbers is the set of numbers 1, 2, 3, 4. There are too many of them to list out, so often we'll use this comma ellipsis notation to say, yep, and so on and so forth in the same fashion. Now, set builder notation is more powerful, and the way we would describe this is, for example, we could say, let's say that W is the set of all elements K. Okay, so this reads as W is the set of all elements K such that K is even. Okay, so there are a lot of even numbers, and this little pipe right here means such that. Some people will use a colon in place of the vertical line, and again, this reads as W is the set of all K such that K is even. So we could also express this in set element notation by saying W equals the set of, well, depending on whether we mean positive or negative, it could be 0, 2, 4, 6, ... and then also negative integers, -2, -4, -6, and ... in that direction as well. So it's much more valuable to simply express in set builder notation, more convenient. When possible. It's not always possible to do that, but when it is, it's more convenient. Okay, so what is a vector space in terms of more mathematical terms? Well, a vector space is a set that we say that the set must be closed under scalar multiplication and addition. So, for instance, this is not a vector space because we're taking some element in here and we perform some operation on it and it ends up in a range. Okay, now in some cases the range and the domain could be the same, but in general, in this case, if I pick an element here, it ends up somewhere else. So let's say that what we do is we have a social security number. That's our domain. And so we have a social security number in here, 1, 2, 3, 4, 5, 6, 7, 8, 9. And that maps over or relates to somebody's name. We'll say that this is Tom Hardy. Okay, so in that case, this is not a vector space because operations that are performed on an element in the domain map to a different set that's in the range. So a vector space is one where if I take an element inside of the domain and I either add it to another element or I scalar multiply it by an element or both, that it ends up still inside of the domain. So in other words, another way of thinking about this is that the domain and the range are the same. Domain is the same as the range. Okay, so the two operations that we have are scalar multiplication and addition. And the reason that we introduce this in linear algebra is because this is where we're dealing strictly with scalar multiplication and addition in the strict sense, meaning that we know what we mean by scalar multiplication and we know what we mean by addition. So let's look at an elementary kind of example. So here's a set builder notation, and this is the set of all vectors containing an element in the top component that we're calling x and an element in the bottom component that we're calling y. And such that x and y are going to both be real numbers. Okay, so what would be examples of elements inside of this set? Well, anything where x and y are real numbers. So we could have 3, 4, we could have 0, -8, we could have 2.6 and 5/3. That would also be an element in this vector, a vector inside of this set. We could have pi and E, Euler's E. We could have basically any rational, irrational, any real number. So is this, and let's give this a name, let's call this V for vector, the set of vectors, is this a vector space? Okay, so vector space is, another way of thinking about this is a special type of set that has certain properties. So scalar multiplication, so if I scalar multiply, let's say alpha equals 2, so, and if I pick an element inside of the set, will it still be an element inside of the set? Well, let's say 3, 4. And if I scalar multiply the vector 3, 4 by 2, I get 6, 8. And is this still inside of the set? Well, yeah, because any vector where both the top component and the bottom component are real numbers is still inside of that set. So in this case, at least this scalar multiplier of 2 produces a vector that's still inside of the set. So basically, if we drew this out and we started off with this vector 3, 4, and we scalar multiplied it by 2 times 3, 4, then we would still end up with a vector that's inside of the set, 6, 8. Does this work for any other alpha? More specifically, this has to work for all alpha, all real numbers alpha. Well, we would be going through a lot of angst if we were picking up all of the alphas, but the types of questions we want to ask ourselves is, for example, alpha equals 0 is a special case. Would that still produce a vector inside of the set? Well, it doesn't really matter what the starting vector is. 0 times anything, any vector is the vector 0, 0. Well, 0 is a real number, and so this is still inside of the set. How about alpha equals pi? Well, pi is a real number, and if I multiply a real number by a real number, I end up with a real number. This is called the closure of the real numbers under multiplication and addition. So pi times anything, let's say pi and e, will produce the elements pi squared and pi times e. Well, pi is a real number, e is a real number. If I multiply a real number by itself, I get a real number, and therefore this works as well. What about addition? What about addition? Well, it turns out that if you add real numbers together, you get real numbers. So 7, 5 plus 2, 8 produces the vector 9, 13. And that is still inside of the set. So once again, we have an example of addition where we do have closure, the vectors that we add together that start inside of the set. Notice that 7, 5 and 2, 8 have to start in the set, and then the result is still in the set. So we have speculation to believe that if you scalar multiply xy, this type of vector, by any alpha, what you end up with is alpha x and alpha y. Well, as long as alpha is a real number, which that's the way we define it, then alpha x is a real number and alpha y is a real number. Real number times real number times real number gives us a real number. Now, so this is a general way to show it. And now let's think about two vectors. If we add them together, let's call them x and let's call them x1 and vector x2 to keep our notation clean. So generically speaking, let's say that x1 are the elements x1, y1, and x2 vector contains x2, y2, the elements. What do we get when we add them together? Well, x1 plus x2 is just x1 plus x2. Y1 plus y2 is y1 plus y2, and now we have to verify, is this vector still inside the set? Well, I started with two real numbers here and here. I started with two real numbers here and here. If I add together two real numbers, I get a real number. If I add together these two real numbers, I get a real number. So it turns out that any vectors that we pick inside of here add together to produce another vector inside of that set. This might seem rather trivial because we are dealing with real numbers and we are dealing with all real numbers. This could get very specific. Perhaps these vectors cannot all be real numbers. Let's consider two other cases. Let's consider the set of all vectors 2k, 3k, where k is a real number. Okay, so what does this mean? Well, this means that as long as there is a ratio of 3 to 2 between the two components, the bottom component divided by the top component, then we have a vector inside of the set. So the first way to start off is just to think about this intuitively. I'm starting with a set, which I'm going to call V, and the vectors inside of the set are such that we have some number k that scales 2 and that same value k that scales 3. So for example, elements in this set would be the element 2, 3. That would be the case where k equals 1. If k equals, let's say, -3, then that leads to the vector of -6 and -9. So these are both elements that live inside of V. So I'll say live inside V, that's their home. Any vector that has this property, 2, 3, -6, -9, 2, we could have 2 pi and 3 pi. These would also be, this would be the case where k equals pi. So any multiple of 2 and 3 in the horizontal and vertical component would work. Now, what does this mean in 2 dimensions? Well, in 2 dimensions, this is any vector, for example, 2, 3. That would be the vector that would be a vector inside of the set. Any multiple of that would be, so that means that any vector that lies along this line, specifically that the y component, what we'll call this component here, as long as that is equal to 2/3 of x. Or we could say that as long as the x component is 3/2 of y. So any vector along this line would be a vector in this set. Why would we be interested in this? Well, because this could actually mean the linear function y equals 2/3 x. So if I scale a vector that's inside of this set, let's say, for example, I pick alpha equals alpha equals 0. Okay, special cases are always the clincher.